Hello everybody, and welcome to today's lecture number 6. Today will be a little more practical to get to really be able to tune some neural networks, and then it'll become even more practical with the introduction of recurrent neural networks. Those are super exciting because it's likely the method of choice for a lot of different tasks, and it will set us up to get to the most exciting and interesting models that people in research are working on right now. So I'll start with just another explanation of backpropagation. Just to, I know that sometimes different explanations work better with different people, and so I think it's good to just look at it one more time in another visualization, another explanation, and then we'll mostly focus on practical tips and tricks to really train a neural network in a way that will get us great performance. Are there any organizational questions about the problem set? Anything else? I was very happy to have had a lot of folks in the office hour on Monday. Again, I encourage you all to stop by. We can start brainstorming your project ideas, your data sets that you could work on, and so on. Cool. All right. So, backpropagation, yet another explanation. So, in general, we'll always want to just compute the gradient of each example with respect to our parameters. So, again, major piece here is just using the chain rule and not replicating computation. And in general, one really good theoretical property of neural nets is that whenever computing your loss for a given example and a set of parameters of your neural network is an O of n, then the computing the gradient is also going to be an O of n. So unlike kernel methods, if you're familiar with those, they can sometimes be quadratic in the number of examples that you have for training, and that would never scale to the kinds of data sets that we have nowadays that get into the millions and hundreds of millions. You could never train something that has quadratic complexity in a number of input samples. And so really it's about the chain rule. We will always have a feed-forward or fprop computation where we start with some input x, we'll compute some intermediate representation y, and forward propagation to get to some z, and then in backpropagation we just go backwards through that computational graph. And so if we just had a single parameter y in between x and z, then this would be the chain rule. In many cases we'll have multiple paths, and so when that is the case and we want to get through these multiple paths to a single input, then we will just sum up the partials here with respect to each of the intermediate inputs. So again, it'll just be the computation fprop and backprop, or forward propagation and backpropagation. And in general, as we have multiple of these, we'll have this general sum over all the intermediate nodes at the previous layer. And we can describe this as a general sort of flow or computational graph, which will be any directed acyclic graph, where at every node we'll have some computational result, and every arc will be some kind of computational dependency. And that will be also the viewpoint that we'll take in next week's lecture when we introduce TensorFlow to you. In TensorFlow, what you'll be able to do is just define any such computational graph, and many of the ones that we'll look at will be standard neural network type architectures. But the amazing thing is that once you define this in this form, you'll also be able to automate backpropagation. Yeah.
Does TensorFlow do backpropagation in an efficient way? Like, so like, let's say a logistic unit, does it do the logistic times 1 minus logistic? Or does it actually have to go through the whole equation?
So if for many of the basic Lego blocks, it does something pretty smart. So softmax, for instance, logistic regression and cross-entropy error, those are basic building blocks that it has where it does the smart thing.
Can you define the fast derivative of anything that you come up with?
Yes, but I mean, in general, it's an open source framework, so you can modify it, but it's like the more complex and the more out there it is, the more complex it will be to do it. But for almost all the computation that we look at in this class, you will be able to use TensorFlow as is. So even the most complex model that we'll get to sort of in the last couple of weeks of the class, like dynamic memory networks or neural Turing machine type networks, those can be implemented in TensorFlow quite easily. And so this is yet another visualization where we have some input x and y, a label y, and you can also write the computational graph or the flow graph in this kind of way where you include, for instance, your negative log likelihood here for your cross entropy, error computation, and then you will basically go backwards. You don't usually update your label, of course, the label y that we want to predict, but you go backwards through the graph in your derivative computation. So yeah, this is basically all of the neural net models that we'll capture. Some forward propagation going in some topological sorted order through this computational graph and backwards. So far we've had some very simple two-layer neural networks, but if you keep this in mind and you keep the derivations in mind, then you will see how basically error messages are just basically being propagated through the network as you try to train it. In the exact same order, reversed to how we computed forward propagation. And like I just mentioned, the nice thing is once you define your forward propagation in your network, and it's just simple matrix multiplications and things like that, or convolutions and other kinds of operations, you can basically completely deterministically infer how to do backpropagation. And because of that, we can have symbolic expressions that we'll define in these flow graphs, and then we can automate the entire training procedure. So last year, TensorFlow wasn't out yet, and so in the class I really asked everybody to implement these models in all their gory details to really get it. I think now we did that in problem set 1 because I wanted you to understand really what it means when we call backprop. But moving on, starting in the next problem set, a lot of this will be automated for you. And so with that in mind, also last year it was much more impressive if somebody took a complex recurrent neural network like the ones we'll introduce in next week's lecture and implemented it from scratch with just basic Python. Doing that in TensorFlow will basically be a copy and paste from some code on the web and just taking the standard TensorFlow implementation. So in some ways it ups all of your games, but it will also make it less impressive to just take a standard model and apply it to a standard data set, which will probably result also in just you being able to do more cool new models and applying it to new interesting tasks. All right, now despite that, we still want to understand how to really tune the models, and not everything, of course, is going to be automated. And so I'm going to go through a couple of really neat tips and tricks. Some are sort of more high level, like doing multitask learning. Others are pretty low level, but are also very important, and they're going to be design decisions that you still won't be make automatically. So let's start with a very powerful technique, which we already kind of talked about a little bit, but only in terms of word vectors. So oftentimes we took word vectors, we trained them unsupervised based on the concurrent statistics, or the just general context windows, and then we took those vectors and we actually started another model, the window model, for instance, for named entity recognition, with those weights. Now it turns out you can do the same thing, but not just for the word vectors, but also for other higher layers that you might use. So here, for instance, we may have our standard window model where we might want to compute the, again, named entity tags or sentiment or whatever, any kind of label you can think of for a specific word. And then we have, for instance, the softmax classifier. And now what we can do is we can not just share the word vectors X, but we can also share the intermediate layers between different tasks, and then only basically change the top layer. And so as you would train this, you'd basically take the softmax here and you have a different weight for this softmax, but you share the weights of the intermediate layers. So only you have basically the overall cost function or objective function will be the sum of the cross-entropy errors for this classification problem plus that classification problem. And there will be some Okay, it really wants me to get on the internet. I'll get on the internet. All right. Now, you can think of how to implement this in a very efficient way. One inefficient way would be we just take the cross-entry pairs here, propagate it, and that's it. But when you think about it a little bit, and let's say you try to do named entity recognition and part-of-speech tagging, so trying to find, again, locations, organizations, and people names, but also understand whether something is a determiner, an adjective, a noun, and so on. And so what you'll end up seeing if you try to write all this out in the math, and you try to see where is computation again being repeated, then what you'll notice is you can actually take the delta error messages that you get from one softmax and from the other softmax, and you can sum those up and then backpropagate both of them. In the end, this will again just be a computational flow graph that has two different outputs, but they come to the same input. And so you can combine the error messages simply additively, and I encourage you all to think through what it would mean having these two different softmax units on top of the same neural network, and then see where in your equations you notice that the delta messages can just be added. It's going to be a very useful exercise. So for word vectors and also some of this pre-training of higher layers, we can see here that that makes a big difference. So the previous state-of-the-art methods that weren't using deep learning, for instance, and these are two tasks that are very, very optimized. So hundreds, or in some cases even thousands of researchers worked on part-of-speech tagging on this exact data set and manually tuned features. And so if you just took a standard supervised neural network and you trained it, it got close but didn't beat human performance and human engineered features from over 2 decades in the case of part-of-speech tagging. And I think about half a decade or 8 years or so in the case of NER. But if you took the word vectors and you pre-trained those, then you actually got fairly close to the human engineered features, especially for named entity recognition. There's a big jump between just training on the task by itself versus training on the task but having initialized the word vectors from the unsupervised task that we described. And those word vectors weren't also the most ideal word vectors. We now have even better ones like word to vec and glove, and so there the results are even better. Basically all of these models are now dominated in terms of performance by neural network models. But just when the first deep learning papers came out, they still had to have a couple of handcrafted features. They're simpler, so you basically had special embeddings for part-of-speech tags, and you had so-called gazetteer features. Now, gazetteer features really sound like a cheat, but basically if you do named entity recognition and you try to find all the locations and people names and company names, gazetteers are essentially lists of states, cities, and countries, of which there are only finitely many. And so if you have an extra list of all the things you're trying to find, then all the model has to do is, in some cases, disambiguate. You know, whether it's this Paris, the person, or this Paris, the city. But it knows that Paris is, for sure, either a celebrity or a location already. So gazetteers are basically just lists of locations and people names and so on. And yeah, we basically, once they tuned their neural networks a little bit better, then in the end, this first paper, or extension of the first paper from 2008, so Colbert and Weston started in 2008 to really work on deep learning for multitask learning, for solving different kinds of tasks like part-of-speech tagging, named entity recognition, and others. And after they tuned their system a little bit more, they did indeed outperform some of the best methods out there. All right, now let's move on to some general strategies for training, successfully training neural networks. These are, I think, some of the good high-level steps that you want to repeat in almost every neural network project, and several of them generalize to any machine learning project. So the first thing you want to do is you want to select the network structure that you have. And so far we've looked at single words, which rarely is the end task that you might care about in the real world. Then you have the option to look at fixed windows. You often, when you can determine what you want to classify for a single word based on just the local context, then a fixed window is enough. It turns out part of speech tagging, for instance, it gets you to almost state of the art if you just look at the 3 words before and the 3 words after. All the other context around a word is not that useful for part of speech tagging. It's a relatively simple task. But if you want to do, for instance, named entity recognition or harder tasks like semantic role labeling, where you want to understand this is an agent and this is an instrument and things like that, then it makes much more sense to take into consideration a broader context. So then we might want to look at sentence-based models. You can also look at document-level models, where you try to, for instance, have a bag of words kind of representation where you just average all the word vectors from a longer document. And then there's some other models that we'll cover later in the class, like recursive or recurrent or convolutional neural nets. Once you define those, often one sub-decision is what kind of nonlinearity you use. Sometimes, for some of these models, the choice will be very clear. In others, you might still want to basically see this as a hyperparameter and then choose the right one. So let's step into the options for some of the nonlinearities before we go to the other steps. So far we've only talked about the sigmoid. The sigmoid is in many cases not the optimal nonlinearity to use. It just, in terms of the optimization, it's not as good. Another better one that you'll see in more papers is the hyperbolic tangent functions, or tanh function. Oh, it's a bummer, it's very hard to see. But basically, it looks somewhat similar to the sigmoid, but it's not, instead of mapping numbers to be between 0 and 1, it'll map them to be between -1 and 1. And just like the sigmoid, what you observe here is that the derivative of the tanh can also be written in terms of just the tanh. And that will make the computation a lot faster. Because in backprop, remember we had at some point, we always have to have the f prime of z, our activations here from the linear layer. And if you can compute that with this simple computation, instead of having to take another exponent or sine function or whatever, it speeds up the computation significantly. And so you might think, well, there's not that much difference here, because technically tanh is just a rescaled and shifted sigmoid. So if you can get to the tanh with just multiplying by 2 the output of a logistic whose input was also multiplied by 2, and you subtract 1. So in theory, they should be fairly similar, but in practice, the optimization for tanh behaves much better. Now, what you'll see a lot in the future will actually be the rectified linear unit. So the rectified linear unit is a very, very simple nonlinearity that is basically just max of your output from the linear layer and 0. So this is what it looks like. Very simple, just linear and 0. So basically sometimes that unit is just completely off, and if not, then it's just a linear output. So just having this max function instead of a completely linear thing makes all the difference. It turns out that when you stack a bunch of rectified linear units, you also get a general function approximator. You can approximate any kind of function. And the beauty of this is that once you're in this linear regime, you won't have the so-called vanishing gradient problem, which we'll cover in a future class too. But basically, on a high level, intuitively, once you're in some of the regiment here, as you train more and more, the derivatives for both the tanh and the sigmoid are often below or smaller than 1. And then you're going to multiply in your backprop computation numbers that are smaller than 1 each time you go through your network. And as you go deeper and deeper in your backpropagation derivatives, at some point after multiplying numbers that are smaller than 1 enough times, the derivative is close to 0. And so there's no error signal that arrives at the lower layers. And the beauty of the rectified linear unit is really that it doesn't have that problem. Now, I think I've mentioned this before, but gradient checks are the most wonderful thing if you actually implement a new neural network architecture completely from scratch. Basically, whenever you think you have your forward propagation at least correct, then gradient checks will basically be able to guarantee you that you did not have a bug in your back propagation implementation, which is rare for a lot of other kinds of machine learning models, like graphical models or others. So basically, all you do is you implement the finite difference computation by going through all the parameters of your network, adding and subtracting a small epsilon, and using the straightforward definition of what a gradient is, and then you can compare this estimated derivative with your derived one, and as long as they're close enough to one another, you can basically know that your computation and your derivatives and your implementation are correct. Now there's one small caveat to that. If you implement your forward propagation incorrectly, and then you make just the right kind of error in your back propagation, then maybe the two will cancel out and you still think it's correct. But in most cases, this will catch bugs for very novel implementations. Cool. Okay, now if you actually have a complex neural network model and you really want to understand all its details and visualize everything very carefully, and you implement your model, and now your gradient check fails, and it's just everything is wrong. Usually what you'll observe is you'll have your long theta vector, and sometimes only some of the blocks are wrong that come from different W's, different parameters of various layers. But sometimes everything is wrong, and you just don't know how to start, right? Because if you have one error in the top of your derivatives, in the top layer, and it back propagates all the wrong things into all the other layers, then everything will be kind of wrong. And so one really great way to help you debug your models, both very conceptually but also just in terms of the implementation, is to create a very small synthetic model and data set. So basically you will simplify your model to the extent possible. Like you may start with the simplest thing, like just having a softmax on a fixed vector. Right? That's basically just standard logistic regression. You make sure that that is correct. And then you might say, all right, now let's backpropagate into the word vectors. Maybe you had a bug in how you derive, pull out the word vector from your general word matrix, word vector matrix. And then you train both jointly and you see if there's some issue with joint training. Then you might add a single unit in one hidden layer. And then you might add multiple units, then you add the bias term, then you might add multiple layers after that, multiple units for those layers. And at the end, you have one softmax on top, and then maybe if you want to do multitask training, you might add another softmax to the top. And that's basically how you can start from the simplest building blocks and then go on top. And this might sound rather trivial, but I wish I had known this when I started my PhD, because I lost weeks of time by not following these steps. So it's really useful. All right, so let's say you chose the right model for your task, chose the right nonlinearities for your model, you implemented gradients, and the gradients are correct. Now you need to initialize your parameters. And parameter initialization is super crucial for neural nets. Basically, we covered this just briefly before in the class, but let's assume you have a nonlinearity, and let's say you have the 10H, and now let's say this is just one unit. This is f of z. And now z here was just w of the, let's say this is zi. You compute your activation ai. And zi was just wi dot. So that was already a row vector, so we just have this inner product here plus the bias term for the ith unit. Now, what happens if, let's say, your x numbers are all in the reals, and let's say each xj is somewhere between minus 100 and 100.
Can you slide the paper up a bit?
Oh, thanks. So, and your W numbers, W, J, K, is somewhere between, let's say, minus 1 and 1. And let's say your BI is, let's say, also crazy high. So B, I guess J here, or it doesn't really matter. BI is somewhere also between minus 100 and 100. Something crazy large like that. Now, what happens when you multiply just at the beginning of training? You haven't really trained anything, but this is how you initialized your parameters. Because you're crazy and we haven't gone to it yet. So where would AI, come out at? Statistically speaking, roughly, sometimes. Worst case scenario. Let's say we have a 10H unit here. So F, so this is 10H CI. Now, where in the worst case would, at initialization, the first time you do forward propagation, where could they come out? That's right. Close to minus 1, somewhere over here, or somewhere over here. And so what's the gradient in those locations? Sorry again?
Close to 0.
That's right, it's close to 0. And so when that happens, and we can often visualize some very high dimensional, very complex function, then and you might want to optimize this. Well, maybe you just initialize it here, and now it's basically already stuck and won't ever get to a better local optimum that may have been down here somewhere. And because the gradient is already 0, it's already stuck. You can't even get anywhere better, right? And so that's why it's very important to initialize. To basically, the first thing you want to do is you want to make sure that as you initialize your parameters, that your x inputs are somewhere in a small range, and you normalize it. And especially if you use 10H units. And then you want to initialize your matrix W and all the elements Wij such that in the first computation you end up somewhere roughly in this linear regime of your nonlinearity. And you can visualize this too, right? You can initialize your weights, you look at the activation of the first layer after the first forward propagation, nothing is trained yet, and you can check what the numbers are for your activations. And if they're roughly in this linear regime, then you know that you're in this complex optimization, you are more likely to have initialized it somewhere here, and you might get to a much better local optimum. So it's a super, super crucial. We'll come to, we'll have a special slide just on like how to initialize specific type of networks like recurrent neural networks, and it can make all the difference between your model basically not training anything and being completely useless, and you thinking, oh, it's the wrong model, why isn't it working, and like you getting a really good performance. And so people have looked at this a lot, and for instance, for sigmoid units, people want to often make sure, one, they initialize the biases to be 0, and then also try to have a mean 0, so you can normalize your inputs to have a mean 0 and a small standard deviation. And we often initialize the weights to be uniform between two small numbers. And often what people use is, for instance, the square root of 6 over fan-in, which is the elements, the number of units that are coming into a layer, plus fan-out, which is the number of units that are coming out of that layer. And really all it does is for sigmoid units, or for 10H units here, that you end up in that linear regime of your nonlinearity. Sometimes the numbers here are 4 times bigger when you have sigmoid units, and again, you just want to end up in that linear regime of the sigmoid unit. So just somewhere close to this area when you start your optimization. Now, a beautiful thing about the rectified linear units is because they're just linear, you just want to make sure that they don't all start in the 0 part, where they're basically dead. You want to make sure they start also in a linear regime, but it's much easier to do for rectified linear units because you don't have the problem on the large values of the inputs. All right, any questions around initialization? So how do you adjust the weights if they're not like that? Well, if you start, you define what they are. So you can look at the visualization and maybe you have some new type of neural network activation function, maybe you have something really interesting that you just want to try and see how it works. What you can always do is you initialize them to small random numbers between minus r and r here, and then you look at what the activation is in the first layer, and if it's too large, you just make r smaller. And that way you make sure that they get to be in the right area. Oh, for ReLU. So for ReLU is one trick to make sure that you end up not having them all be small is you can actually have the bias to be initialized also a little bit in a positive number. That way you start out for sure in the positive part of the value. And otherwise you still use relatively small numbers just because you don't want them to blow up like crazy. Cool. All right, so stochastic gradient descent, how do you actually optimize this? And those will also be hyperparameters and options for you in TensorFlow. So TensorFlow isn't going to automate everything. So these are all still really important tricks. So basically, we talked about general gradient descent, where you take the entire gradients with respect to your entire training data set. So full batch training is never the right solution. What we then looked at was completely stochastic gradient descent, where you might look at only a single data point, a single window, for instance, one at a time. And that is definitely the better end of the extreme spectrum. Again, never use full batch methods with neural networks where you compute the entire derivatives over the entire training set. You could sometimes use second order methods, but they actually have been somewhat out of favor. And what is much better are other techniques like momentum, which we'll talk about in the next couple of slides. So in very few cases will it be necessary to basically use LBFGS or conjugate gradient methods, where you may need to approximate the second order derivatives with a lot of computation. Now, what is really useful is to actually do mini batch stochastic gradient descent. So instead of looking at a single window, which is on the one extreme, instead of looking at all of the windows, which is on the other extreme, or all the data examples that you have in training, you actually go somewhere in between and you look at 20 or 100 different training examples before you make one update step. And so the beautiful thing when you do that is, and often you can concatenate all your inputs in some principled way, and you can multiply your activations and your W parameters of each layer with all of them in one large matrix multiplication. So what do I mean by this? So in many cases, we'll have some computation W times X, right, to compute some kind of Z. Now, that is, at least you can parallelize it, because to compute each unit here, you multiply this by this, and this again by this, but they're all independent, right? So in theory, you could multiply this one in parallel with this one. Does that make sense, that visualization? Now, what's actually better is if you had a W here, because it takes time to set that up in general in the computation. Instead of having just one X here for your first training example, you can have multiple X's, and you have a very large matrix of X inputs. And now you can parallelize not just these computations across one X, but also across all the other X's. So instead of having computing x1, x2, and x3 one at a time, you can have one large matrix where you concatenate all these vectors into one larger matrix, and these are all the same, and basically parallelize like that. So now you only have to give one set of training data to your GPU or your parallel multi-core CPU, and it can parallelize across all these different computations. And if you have, for instance, a GPU which has 5,000 cores, and there's overhead of copying from your CPU RAM to your GPU memory, it'll be very, very efficient to have larger and larger matrix multiplications. So that's one of the advantages of using mini batches. It still has a lot of the stochasticity and the changing landscape of your objective function that prevents you from getting stuck in a local optimum, but you can use some of the parallelization from having the computation of multiple gradients for multiple different inputs. Does that make sense? Are there any questions around that? That is basically the default that you almost always want to use, is some kind of mini batched stochastic gradient descent. Cool. Now we can further optimize or improve over standard stochastic gradient descent by having momentum, and that plays nicely with whatever mini batch size you use. But basically the idea is to add some friction or fraction v of the previous update to your current one. So basically, when your gradient keeps pointing in the same directions from one mini batch to the next mini batch, or from one window to the next window, this will essentially increase the size that the steps are taken towards the minimum. And another way you can look at it is also that it will reduce, what you want to do when you do this, because you keep adding something to your updates, you also want to reduce your global learning rate that we have in general. So if we use this one here in general, we have alpha. If you now, instead of updating directly your parameters with alpha, you use this v term, you want to have a small alpha, because you keep adding to it. Often what we basically do here is we have this update rule v, and we have a hyperparameter mu. Sometimes you start with larger mu's, and then you with smaller mu's, and then you keep increasing it until you get close to 1. And then you update your parameters data with this. Now, this is not super intuitive when you just look at the equation, so let's look at a geometric interpretation. If your gradient would just point in this direction, but maybe in the previous time steps you had a v that points in this direction, then your actual step will be the sum here. And you can kind of think of this as a friction. So if you had optimized something and your gradient points into a valley, you might not want to overshoot out of that valley in your highly non-convex optimization landscape. And also the parameters will build up velocity in some interpretation in the direction of the consistent gradient. So here's a great visualization when you optimize with pure SGD versus with momentum SGD. So it's a very simple function, but it's in some cases tricky because it has this sort of valley, right? So these are the level sets. You can kind of think of this as a bowl that is very, very wide, but also very narrow. And so if you look at the gradient, let's say you try to minimize this here, the gradient here points into this direction, right? You have the bowl that is very, very narrow, and so as you go, you basically go and overshoot a little bit and you get stuck in the other side of the valley. Now with momentum, you'll kind of average the directions from the previous time steps, and so it'll basically point towards the minimum much more quickly, and you'll optimize that function and get out of that narrow valley much more quickly and go in the right direction. Now in this case, we assume that alpha is always fixed, but this momentum term, which in physics term is much more of a friction term than a momentum term, but this basically changes. Now what we can also do on top of that, which is very, very useful, is actually change the learning rate itself over time. So the default would just keep having the same alpha, the same learning rate or step size here to be fixed across our optimization. One important term here that I may not write down here is an epoch or epic. Some people pronounce it differently. It's spelled E-P-O-C-H. I say epoch. And an epoch is essentially one pass over your entire training corpus. So if you have 1,000 training examples, it's going once over all 1,000 training examples. Now, what we may often do instead is we actually change the learning rate and we decrease it. So you might, for instance, what's quite commonly done is reduce the learning rate alpha here, the step size again, by 0.5 once the validation error stops improving. So what does that mean? We can visualize that, and I encourage you all to visualize furiously and very often what your model is training. So let's say this one here is your error, and you have a training error, and let's say your training error keeps going down, and this is the number of iterations. And now we basically observe, okay, in the beginning our training error goes down, and oftentimes we'll have some validation error as well. So maybe we'll use this here. And our validation error goes down too, but now maybe they both kind of flatten out. And you observe this, so this is training error. And this is our validation error. And now we observe that it flattens out. And we're great, and this is usually, if you have many batches, it'll be much noisier. So let's say it's sort of the average. Now, once we see this, and now because training, let's say you're training on a very large corpus and you don't want to wait because the deadline will come soon, right? And you can't wait for another 2 or 3 days to see what happens. As soon as you see that your validation error kind of flattens out in your visualization, it's usually a good time to reduce your learning rate. And so if you now change and your alpha mu is just, let's say, 0.5 of your previous alpha and the learning rate after you had maybe run 3 epochs or just half an epoch, depending on how large your data set is, what you often observe is something amazing, which is the next, after training again and continuing to train, but with a smaller learning rate, you'll actually see a big dip in the error, in your validation error. And that seems to be relatively consistent for especially convolutional neural networks, but also other kinds of deep learning models. So yeah, super useful to change your learning rate. The smaller your data set is, the less that matters. But once you want to train over all of ImageNet or a very large corpus, this is super useful. There are a couple of other, yeah?
So do you see that because with the large learning rate you were actually just like jumping over points of minimum?
That's one intuition, yeah. So one intuition is if you have a large learning rate in the very beginning, you just want to explore your energy landscape or your optimization landscape more broadly, but then afterwards you might start missing out on having more carefully fined local optima that are smaller and harder to find and easier to sort of jump over with general SGD. Yeah.
Does that TensorFlow have functionality to change your learning rate in real time?
TensorFlow has lots of fun options for optimization. So it has momentum and so on as options. And definitely it has also great visualizations that show you sort of the errors that you have and so on. All right, now those are some options. There's an even better one for a lot of NLP problems, which is AdaGrad, or adaptive subgradient methods for online learning and stochastic optimization. It's a great paper that's introduced by John Ducey in 2010. I think he's now a professor here in the stats department. His idea, and it's in some ways a continuation of some other folks, is to actually adaptively change your learning rate for every single one of your parameters. And this is going to be super helpful if you have certain parameters that are used much more infrequently than others. So let's say, for instance, you update your word vectors in your large optimization problem. And now you have certain words like the and a and his and he and she and so on that you see in almost every other training example. And then you have another word like zebra or aardvark or some really rare words that you see only once. Now intuitively what you'd want to do is when you see a word only once or twice in your whole training corpus, you want to really update it with the one thing you just learned about it. You want to make a larger update step for those word vectors. You want to have smaller update steps for word vectors you see all the time, because you don't want to have those be jumping around constantly. After a while, you just kind of realize the is a determiner. It's usually in front of other nouns, and it's not that. You don't learn that much more useful stuff about it after you've trained word vectors for like an hour. And so that's essentially an idea that is used here. And so the way they use this or implement this, and there's lots of nice theory behind it. If you're into theory, I encourage you to read this paper. Is basically you keep track of the current sum that you've had at all past training steps for a specific parameter. So you compute this G here, which is essentially for each element. So at the time step t of your iteration, you have for the ith element of your theta vector, you have some partial derivative here. And you keep track of those and you basically sum up all of them from past time steps. And so intuitively here, if you have the, for instance, it happens in every other window, this sum will get very large, and so the learning rate for that parameter gets smaller and smaller. Now there's...
You keep track of all the gradients, you just can keep track of the sum of squares?
That's exactly right. So here, so this is the sort of theoretical equation, but of course you notice you don't really need to have access to all the past ones. You can just keep track of the sum of squares. Now, there's some folks who then said, well, but after a while, you may get also stuck in a local optimum, and now you can never update that parameter again. So now there are various variants of this idea where you essentially say, well, let's not take let's maybe have this whole sum, but every other epoch, maybe after 4 epochs, we'll reset the sum. And we just kind of allow 100 flowers to bloom again, and we'll explore a little bit broader again. And then we'll let it sum up again and get smaller. And then one of the better methods at Delta actually will have a window, and so you do need to keep track of some of these squares, and you basically keep the sums or just the absolute values, depending on the method, of the last like 50 time steps or something like that, and you basically update it like that. But AdaGrad is also that's a good default. I've used it in lots of papers.
Are these built in?
Some of them are built into TensorFlow, not all of them are. Awesome. So now let's assume you found the right network structure, you implemented it correctly, you know you implemented it correctly because you either use TensorFlow or you checked with finite difference gradient check. You optimize it properly, you visualized your activations, and you know it's doing the right thing, at least when you start optimizing, and you carefully visualized your training and your validation error, and your training error is getting smaller and smaller, but at some point your validation error stopped improving, stopped decreasing, and it's kind of plateauing in a still relatively high state. But your training error went down almost all the way, and you have 99% training accuracy. You basically can, whenever you see an input from your training data, you classify it correctly. That's basically the point where you say, all right, the model, and these models are very powerful, and they're able to almost memorize all your inputs. There's a good rule of thumb there too, which is if you have more parameters than training examples, then your model is much more likely to be able to just memorize all your training examples. But the more it memorizes, the less it generalizes in many cases. Not always, but often. And so when that's the case, it's time to regularize. And a lot of the breakthroughs that enabled deep learning to work better and better over time also came through better regularization methods. So the simplest one, and the first step, could be to just reduce your model size. So maybe you have too many parameters, you don't need that many to get to a reasonably good performance, so you could just take out some layers or reduce the number of units at each layer. That's a relatively simple tool. The second one we already covered as well. You kind of assume you have a prior on your weights, and you have a simple L2 regularization term on them. Sometimes regularization is called weight decay also in deep learning papers. And another trick is actually early stopping. Maybe you have the right number of parameters, but if you let it train for too long, it'll overfit and you just stop after a certain amount of time. And you can use the best validation error to find out when to stop. So one very common technique that I've used a lot and a lot of people do is you actually keep your weights for the last 50 iterations, and every one epoch, for instance, depending on how large your data set is. If your data set is smaller, you can use every 5 epochs. If you have a very large data set like ImageNet, maybe you look at every 1/3 of an epoch. Then you save all your weights and you look at your validation error. And you do that for a day or 2 or 3 days, depending on how large your training data set is. And at the end, you just pick the one model that had the best validation error. And that may be the model that you got after 2 days, and maybe the model you got after 3 or 4 days. But just picking your validation, picking that model based on the validation set is a good indicator, as long as you establish that your validation set is useful and large enough to not be super noisy. And there's some other potential constraints you can put onto your activations, like sparsity constraints, but they're not used as much anymore, so maybe we won't go into too many details. One way to prevent overfitting, or so-called feature co-adaptation, where you basically have certain features fire only when they exactly see a specific combination of inputs, is called dropout. It's a very popular technique, has a lot of nice theory that was, not used to invent it. Jeff Hinton, who invented this, has just phenomenal intuition, but afterwards a lot of people analyzed it and tried to come up with interesting theory of why it worked so well. But basically the main idea is that at training time you will just randomly delete 50% of your inputs and set those neurons to 0. It's basically hurting your model. You're taking out information from your model, because these neural networks are so good at just memorizing everything that if you don't do it, they will memorize exactly this input, these sets of pixels, and exactly this constellation will give you exactly this output. Now if you start deleting some, intuitively the model can't overfit and just memorize exactly that input. It has to get used to seeing noise. So you basically delete 50% of the neurons at each layer. And then at test time, you of course never want to delete any of your data at test time. You want to use as much as you can at test time. And now the weights might be twice as large, so you can basically divide all your model weights by 2. And then they're on the right size, the right sort of general activations that come in after your linear layer. And you now have a model that is less overfit and has features that are not fully co-adapted. So yeah, if you had only a single layer, the people have tried dropout even with simpler models like logistic regression. Even there it can help sometimes. And it's in some ways basically an interpolation between having something like naive Bayes, where you have completely independent single features, versus logistic regression, where the weights are set in the context of all the other weights. There's some of the theory explains why this works by saying, well, maybe what you're doing is you're almost training different networks, and in the end you kind of average them in your weights. So it's different kinds of model bagging techniques. But this is one of the really powerful regularizers, and a lot of people who try it in all kinds of ways for different kinds of models. For recurrent neural networks, which we'll cover later today, it doesn't work as well as for convolutional neural nets and other network types. All right, there are some other tips and tricks which we'll get to in later lectures, but these are sort of, I think, some of the most important ones that get you started and that are very useful for your projects already. There's a great paper by Joshua Benjir on some practical recommendations for gradient-based training of deep architectures, where he talks about a lot of other techniques, especially here the main hyperparameters that we also just covered. Generally, in the end, you might end up with a lot of these hyperparameters, and it's kind of daunting. You can't really try the combination of all of them, right? The cross product, if you have, just each hyperparameter, let's assume, had only 2 options, but you have 10 of them, well, it's still 2 of the 10 many experiments you'd have to run to look at all of them. And now, in most cases, actually, they aren't just binary, like this one or that one, they're real numbers, like how much regularization do you want to have? How many units do you want at each layer? So you have usually too many options, and a lot of people tried lots of fancy things on hyperparameter search. Surprising answer is that in many cases, just defining the range in which each of the hyperparameters should be, so let's say layer 1 has somewhere between 10 to 1,000 hidden units. And my regularization is somewhere between 0 and 10. And then just basically randomly selecting values in those ranges works surprisingly well. Better than a lot of other much more sophisticated techniques that then need their own computational cost to be computed. All right, any questions on practicalities of training neural nets? If you have any that come up and you want to look at something, have some weird patterns, feel free to come to office hours. We can look over it. In general, it's always very useful to try to be close to both your data but also to your model. If something weird is happening and you visualize things well, you very often see what the problem is in your visualization. And it's often useful to visualize both some concrete cases and see, oh, if I plug in this text, like all my units seem to be always on, or most of them are always off. What's up with that? That's one way. And if those look good, then, but you still have some issue, you can look at the statistics too. If I do feed-forward propagation of 1,000 sentences, I can look at the statistics of how often are these neurons on or off, and what are their values.
Does TensorFlow allow you to do like neuron level?
It does, yeah. And in fact, there's a beautiful visualization. Maybe I'll go over it next week, where they created a nice web interface last week that was just published. It's very cool. All right, now let's move on to language models and then recurrent neural networks. So language models are a super useful basic tool in natural language processing, and it turns out can be improved significantly with deep learning as well. So on a very high level, all a language model does is it wants to compute a probability for a sequence of words. Fairly straightforward. So let's say I just want to know how likely is this sequence in the English language, for instance. So that might be helpful if you have a machine translation system. That machine translation system might say, well, this word could translate to these 10 other words. And this word could translate to these other 5 words. And now, just simply, you could have 10 times 5 potential translations of these 2 words without any context. But maybe, going home is much more likely of a sequence than going house, right? But both might be coming from the same German word, zu Hause or something. And so that's basically one of the many applications where language models can be useful. So what you'd usually do is you condition on some window of previous words, because it's kind of hard to compute the probabilities for all possible sequences, right? There are basically way too many, and you can't compute, you can't even keep around the counts for all possible word sequences in a language. And so what's very commonly done is you say, well, I will approximate the probability of the next word not conditioned on all the words before, which might be like hundreds or thousands if you have a longer document, but only a specific window size again. And so the window here might be, for instance, M, so I will only look N here, and like noun. I will only look at the N previous words of the current word. Now, I'm not going to go into too many details, but traditionally, if you wanted to train a very powerful language model, it also works better if you have more training data. And if you took standard machine learning techniques where you basically try to keep around counts for as many possible sequences as you can for as large of n or n-grams as possible, you end up with many, many gigabytes of a large file. Right? Because you want to, in order to approximate this here, you can just keep around very simple counts, like how often do I see this word versus all the other words after this sequence of other words. And that's basically boils down to just having a gigantic table of counts of how many times, you know, for all the different combinations. And so that's not very scalable if you want to get to large windows, and larger windows are indeed helpful if you could keep them around. And so one very powerful way to start improving language models was by using neural networks instead of these count-based methods. And so here is basically a model that is something that you now fully understand and can implement yourself. It's just a different visualization to the ones that I've shown you, and I want to expose you to these so you can see kind of that really this is all the same stuff to what we've talked about in previous lectures, but when you actually read papers in the literature, you'll just see different notations and so on. So here, this is the notation that we may have used. So you just have a softmax, and you have a couple of different layers, and X here is your window where you concatenated the word vectors for that window. And the output is still just a softmax, because all you try to do, instead of predicting a class for the center word, you now interpret the softmax to be the probability for the next word given the current window. But it still boils down to a classification problem, right? Now the classes are just all possible words, and each word is its own class. And you predict the current class just happens to be what you're training for to be the next word. And so here is one different way to describe this. We have here the so-called table lookup. That turns out to just be coming from an index. You pull the column of that index to basically get the word vector here. So they describe word vectors as just C. And then you concatenate all of these together, and they will get input to a hidden layer neural network. That's just a 10H. And then you have here a softmax, and now instead of having just 2 or 3 classes that we might have in named entity recognition, you have a lot of classes, because it's basically the size of your vocabulary as the output. And that's just the probability for the next word at time step t being exactly this word ID, given this context of the previous n words. So now with the simple window model that we've had, we could implement a simple first language model that predicts always the next word, and that we could use as a nice tool to find weird sequences in our input, or to find reasonable translations based on a set of candidate translations. We could literally have an entire lecture on just language models, so this was pretty condensed. Are there any questions? Yeah.
How many units are in the layer?
It highly depends. I think you want to have at least a couple hundred here. I think like 500 or so. Oh, and these are the original equations. So instead of, I want to make sure we're consistent so you're not too confused. So in our notation it would be this, but if you saw this paper, they would be writing it like this. But basically it's the exact same thing. You have here your softmax, your exponents, and they just write out the the layers with different capital letters for the matrices at the various hidden layers. Okay, now the problem with this, and with a lot of other language models of the traditional type where you keep the context and the counts for specific n-gram lengths, is that you're always conditioning only on the last n words. And in very few cases can n go larger than 5. You can't keep around the counts for all 5 grams. There are a lot of different 5 grams in the English language, right? So just some simple math. Let's say you have a vocabulary size of 40,000 different words, and you want to now look at, just compute how often do you see all possible bigrams. Of course, they don't all appear, but that would be 40,000 to the power of 5. Many counts to keep around in the traditional models. And here we also basically only have the first previous n words. Now they're word vectors, which is much more useful. This will require much less RAM to keep around the model, but it's still kind of a fixed window. And maybe n+1, the 7th word before the current word, was the one that might give us a much better indication of which word might be next. So maybe there was a story such as there is a big series of wars in Spain, and then 2 years later the big battle off happened or something. And now, having seen Spain a couple of words before makes it much more likely to have a battle off like Madrid or some other Barcelona or some other Spanish city or French city or somewhere where Spain may have had wars. And that might always be in the context that is just before a fixed window. And this is one of the many good motivations to look into recurrent neural networks. So recurrent neural networks are super exciting because really that's where research is at right now. A lot of folks are doing research. A lot of the models that you might use on your phone when you use speech recognition on your Google phone will use recurrent neural networks. They're in a lot of different places in search engines and in other places. So let's look at the basic definition of a recurrent neural network. Again, I'll expose you to a couple of different visualizations, but for next slide or 2 slides, they're always the exact same model, just visualized differently. So in the end, the equations are usually the best way to disambiguate it. But in our original visualization of neural networks, we basically have here word vectors again at every time step. And the word vectors are given as input to a hidden vector computation here, a standard single layer neural network that basically the main reason why they're called recurrent is that we're using the same parameters, the same matrix W for computing the hidden layer activations at each time step. So to compute the time step at t-1, we'll use W, and for t, we could use W, and for t+1 we use the same W. So let's say, for instance, we try to compute a recurrent neural network language model, which is quite common. What we might do, let's say we have here an input sequence of word vectors, x1 to x capital T, for the total number of tokens that we have in our whole training corpus. Now what we will do at a single time step is to compute a first layer, which is basically a standard neural network layer with an activation that's a sigmoid. This could be a 10H2 or rectified linear, it doesn't matter, some F. And we sum up these 2 linear layers. Now, whenever you see this, it's important to keep in mind that you could rewrite this as just a standard layer. So when you have some F of Z1 plus Z2, for instance, and that might be F of W1 times X1 plus W2 times X2. Now you can see this as essentially having a W1 block here and a W2 block, where you basically took each of these matrices and you just concatenated the 2 matrices times the concatenation of these 2 vectors, x1 and x2. Is that intuitive of why those are the same? Basically, here you multiply this to get to the first element of this here. You multiply this times this plus this times this vector. And well, that is exactly what happens here. You multiply this by this plus this by this, right? And so whenever you see a plus, you can think of just having concatenated two inputs together. If this is not intuitive, you should like make sure you write out the indices and see why those come together. All right, so basically here, at each time step, we just have a single layer neural network. And it's the simplest recurrent neural network definition that we have. And xt just happens to be the word vector at the tth time step. So sometimes I use these brackets to determine this, because it's not, in many cases here, this is the time step, but then the time step means that at this time step we have a specific word, and now we have to look up which word vector actually corresponds to that word index. And then to predict our probabilities over all the words, we just have our standard softmax definition. And we will interpret that output to be the probability that the next word, xt plus 1, is exactly that specific index in our vocabulary. And here are just two other definitions and visualizations of that model idea. Sometimes people write it like this, saying this W here is the same computation, or the same W here is used at every time step. Or sometimes you just visualize one time step and you assume that it's the exact same computation at every time step, where the same W hidden is used. So the superscripts here are basically indicating that this is the matrix of parameters that governs how you compute part of the hidden layer based on the previous hidden layer, and this is part of the computation that's used to compute the hidden layer from an input. Yeah.
So to clarify, a time step means a word index within a list of words, or an iteration?
That's a great question. So a time step means exactly at one token in our case, one word. Yeah. So if I have, I like to go, then, I is time step 1, like is time step 2, 2 is time step 3, go is time step 4.
This is just all purely like assuming we have the weights trained and everything. So this isn't we're not worrying about training. This is just assuming a trained model and we plug it in for this problem.
That's correct, yeah. So we assumed here we trained this, but we'll soon get to training, and training is also going to be relatively similar to all the things we've done before. So let's, basically look into some more details here of the recurrent neural network. Main idea again is just we use the same weights, the same set of weights W at every time step. And then everything else is very similar to what we defined in standard neural network notation. One interesting detail here is often how do you initialize the first time step, h. In many cases you just basically set it to 0. And it's often, again, very good to carefully define the dimensionalities of your parameters. So we define here D as D subscript H as the dimensionality of your hidden layer. And so this has to be a square matrix, and then DH has to have the same number of rows, but it can have a different number of columns because the word vectors might have a different dimensionality to your hidden input. They don't have to have the same dimensionality. And WS, in the case of training a language model, is basically a number of rows is the size of your vocabulary, and then times your hidden state. Cool. So how do we train this? Well, it turns out we use the exact same cross-entropy error that we used for classification, which is basically just here the negative of, I guess, the average log probability over our data set. So again, this is just the predicted output from our softmax times the actual true word that will appear at the next time step. And we will sum this over our whole vocabulary, and then we sum at each time step. We basically compute this, and then we basically sum this over all possible time steps. And so one way to evaluate this might also just be saying, well, let's just compute exactly what this loss function is, and then the smaller this is, the better, or sorry, the larger, I guess, the larger the probabilities are that we predict for the correct words, the better. But what's usually more common is to use this in terms of perplexity, which is just 2 to the power of this term. And so in that case, lower is actually better. Now, in theory, we would have all the tools to train this, but if you actually do train it, you'll realize that it gets quite hard. And I think next week we'll have some time to dig into this and look at some mathematical derivation of why this is hard and where Jacobian matrices are coming into play. But basically, intuitively, the problem is you multiply here the same matrix at each time step during backprop. So this is the delta that we carefully, painfully derived most of in the last lecture. And to compute these error signals, delta, at each layer, you have this computation. And now if you have, for instance, the 10H, and your derivatives here might be really small, then that's problematic, right? Because you have small numbers that you multiply at each time step going backwards in time now. And if your W is very large, then you also multiply large numbers with the same large numbers at every time step. And so your deltas can basically both vanish, they become smaller and smaller, and in the end you can't make use of, having seen Spain 10 words before, because the gradient that arrives at Spain is close to 0. But because of W and having the same exact W at each time step during backpropagation, you also may have exploding gradient problems. And so we'll get to exactly what this means and why this is a problem in next week's lecture. But I wanted to make sure that you can now have most of the important tips and tricks to really train something in practice. It might already be useful for your problem sets, and if you can now basically get started on implementing some of the most basic baselines for your projects, and introduce to you on a high level what a recurrent neural network is. And next week it'll get really exciting, because then you will basically go over TensorFlow. Bharath will give a lecture on TensorFlow. He's been working on it a lot in the last couple of months in his research. And then we'll look at even more powerful recurrent neural network variants, like long short-term memories or gated recurrent units. And then those are basically the tools that people are now using in all the top papers. And those are the higher level building blocks for some of the most powerful techniques that are currently out there in the literature. Cool. That's it.